All right, so let's go ahead and talk a little bit about waves. So based on your guys' questions that you had, as well as how you did in the Kahoot, I put together some stuff for you. So what you're looking at here, so I found this GIF that's going to go through and talk a little bit about waves. Also, you have this paper, so it's front and back. So you have this figure, which is just the still version. You have this one here, and you have figure three, and get this out of the way, and figure 4. Okay, so if we look back here at this GIF, if you look, there are areas where the lines appear darker. So this, I'm going to switch gears here a second. So this, what you have on your paper, these lines right here, the darker lines, these are where you have more of the particles or the atoms are all squished together and they're farther apart. Okay, so these, this and this, oops, these are longitudinal waves. Okay, and if you remember, there are two types of waves. We have longitudinal waves and we have transverse waves. Longitudinal waves, the particles that are being, the energy is going through are moving. So you have an overall movement and then you have particle movement. Okay, so the overall movement is always, like, energy is always going to be going in some way. Okay, so your overall movement is going in this direction, but also here you have the wave or the particle movement also going in that direction. So in a longitudinal wave, you have parallel motion. Okay, whereas if you look down here, okay, these two red dots right here, so if I were to be flicking this rope, okay, the overall movement is still going from left to right, but these particles, instead of moving parallel with it, are going to be moving up and down. Okay? All right, so let's take a look down here. You guys did really well on what wavelength is and what crest and what trough is. Okay? But what we need to refresh our memory on is what frequency is. Okay? If you remember, oh, by the way, wavelength, the symbol for wavelength is this funny little kind of upside down Y looking thing. I'll come down here and draw it bigger for you and get this out of the way. Okay, so this, it's like that, go down. That's the symbol for wavelength. It's a Greek or Latin lowercase letter. I can't remember which one it is. Okay, but if I come back up to here, so talking about frequency. Frequency, let me get my thing situated a little bit better. There we go. Frequency is how many wavelengths in a set time. Okay, so if you look at figure 2 here, the set time that they've given you is 1 second, and typically this is what they'll do. Okay, so now a wavelength can be crest to crest, which is how we defined it, but it can also be trough to trough. Or honestly, it can be anywhere in which you have an entire cycle. So here you start up, you go down, and you come back up. So it's gone through its entire wave once. Okay? So if you look over here, the time frame that they've given you, you will go from the trough up and down. So here's one wavelength. One wavelength in 1 second gives you a frequency of 1 hertz. Okay, Hz equals hertz. So this is the unit that they're using to measure frequency. Over here, now earlier today we discovered, hey, wait a second, this line right here doesn't exactly match up with the true bottom of the trough, which is right there. So it's off-site just a little bit, which means, let me use a different color pen here, which means that for a wavelength, I'm going to have to go completely back to this point, say right there, and then by the time this line right here where I meet the line, I haven't gone through a whole nother cycle yet. So you're looking at about 1.5 wavelengths per second, which is going to give you a frequency of 1.5 hertz. Okay, down here at the bottom, same way. Oh yeah, so let's label these waves A, B, and C. So on wave C, I've gone, again, it's not quite at the exact bottom, it's a little bit off center. So I gotta go, here is 1, here's 2, here's 3. It's not quite 4. This is actually incorrect. It is not 3 hertz. It should be 3.5 hertz, okay? Because again, you've gone about half a wavelength when this line stops, okay? So in class today, I gave you a couple questions that you needed to answer. So the first question that you would need to answer for me is, what's the connection between wavelength and frequency? Okay, now remember, another way to ask this, what's the connection? How is this related? How are they similar? What do they have in common? How does one affect the other? Okay, so the second question, the second thing I want you to do is I want you to draw a 10 hertz wave, okay? So if you were to take this section right here and we were to extend this down, okay, let's say you're going to make D. We want to create a 10 hertz wave in this space right here. So you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's pretty darn close, okay? All right, so I've got 1 hertz, 1.5, 3.5, and 10. You should notice some differences between here. So the third thing that I'm going to need you to tell me is, okay, so as frequency increases,
Lane Gray, please come to the front desk. Lane Gray.
okay, so as frequency increases, so as this number gets bigger, okay, wavelength is going to do something, okay? And then you're going to need to tell me why. So as my frequency gets bigger, what happens to my wavelength? Now remember, wavelength is the space from here to here. So I have that. Then I'm going to have here. Here's a wavelength. Here's a wavelength. So what's happening to the wavelength as my frequency increases? As my frequency increases, my wavelength decreases, or it gets smaller. Why? Because I still have this amount of space, this amount of time for the energy to go through. As the wavelengths get smaller, I can fit more of them into that same amount of space. Okay, I hope that makes sense. Okay, the last question is, what's the connection between energy and frequency? Okay, so I'm going to use this graphic to show this to you because I think this helps make it helps things make a lot more sense. Okay, so now remember from up here and from the video the other day with the Bozeman science guy, when you have a wave, what's actually being moved is the energy. So the energy is passing through here. The energy is moving from one point to another. The energy is going through these red dots. The particles or the atoms themselves are going to stay in place. Okay? So let's just say that at this peak right here, the energy level is 10. That really does not look like 10. Okay? So let's just say at each peak there has an energy level of 10. So this part right here, I'm going to have 2 peaks. So I have double the energy. Let's say here, I've got 4 peaks going on here. And if each peak has an energy value of 10, here, I've got all these peaks here, okay? So as the frequency increases, the energy increases, okay? And if I take a look at this, at figure 3, okay? Gamma rays, this is my highest frequency, my highest amount of energy. This is the stuff that you have to have concrete walls blocking you from, okay? This is the stuff that's created in the sun or in the star, in the core of a star. And look how short these wavelengths are. There is an incredible amount of energy there because the frequency is so high. It's like super concentrated. Down here on the opposite side, if this is my highest frequency, this is my lowest or largest. Not largest, let's go smallest frequency, lowest frequency. Okay? And this has my lowest amount of energy. Okay? Also, if you look here, okay, highest frequency, shortest wavelength, shortest wavelength. And on this end, I've got my largest wavelength. Okay? Something else that's kind of a misconception for people as we're looking through this. Okay, so this rainbow right here is this right there. Okay? Radio waves are not red. And this is kind of a misconception, especially with the way this one is drawn. If you look down here, gamma rays are not purple. This belongs in this tiny section right here. Everything over from UV rays to X-rays to gamma rays, those are going to be invisible to us. Our eyes cannot see it because our eyes are not designed to do that. Over here we have infrared, radar, FM. These are all types of radio waves right here. Okay? Again, it is going to be invisible to us. We cannot actually see this type of energy. Now, we have tools that can fit on a camera that can see infrared. We can see the after effects of radar on a screen. We can see the TV show up on the TV through the radio waves, but we are actually not going to see those waves. You're going to see the effect of them, or you're going to see another tool use those. Okay? So I hope this helped kind of clarify things for you. If you have any questions, please let me know.